Thank you, Dr. Monpilai. And next, I would also like to thank my good friend, uh, 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 Jürgen. So thank you for building the bridge between the Thai railway engineering community and part of my working experience. So, low carbon design and construction method for high-speed rail and intercity links. Now, a little bit about my professional experience. I used to design, for most of my professional life, signature bridges, like the Bay Bridge in San Francisco, like the third crossing in the Panama Canal, also Confederation Bridge in Canada. Then I and Jürgen was very, very fortunate to be a colleague. He's working on the construction supervision side. I was working on the design side for our Bang Na Bang Pri Bang Kang job 30 years ago in Bangkok. So this is my third time come to Bangkok. The first time I came here for the Bang Na Bang Pri Bang Kang Expressway. So a little bit about our company. We have a design institution. We also have a digital service company for transportation infrastructure. And we have a couple of offices, one of them in Hong Kong. Then what we do, basically bridge and the structures for transportation. Anything structures for the station, underground, or bridges. Now we also have the beam, of course, international project reconstruction too. Then we have engineering IT, smart monitoring, and mass data visualization. That's two independent companies under Sun Engineering, Sun International Consulting. Now that's what we do in terms of a professional service to our client. I wouldn't want to repeat it. Basically, almost a life cycle without physically contracting. So today, I want to present you with a different way to think about your bridge. There is a better way for railway bridge. So a little bit of overview about bridge engineering in China, in a sense, probably in the world. Well, as you know, I wouldn't want to go through the specific number. I think if you do an integration for the past 20 years, in China, they built bridges, the total number of bridges equal to of the rest of the world combined. Even more, to be honest. So whatever they're doing pretty much reflect what's happening. Now, that's some of the bridges that I participate in, some as a design, other as a consultant. It's all big ones. We did probably 500 bridges in 20 years, major bridges. But in the past 10 years, I started to concentrate on the main mid-short span bridges. Why? I found out as I went back to China, 80% of a bridge, or even 90%, are short span. The investment of short span bridge occupy, you know how much for high-speed rail? 45% of the total investment. Think about it. But it was designed lousy. Let me tell you why. All the big shot designer, so-called world-class designer, they can care less about the 30-meter span bridge. You know, big institution. They just copy the drawings from 30 years ago, 20 years ago. Copy, copy, copy. Amazing. But that's where you make a difference. So I decided to give up my signature bridge professional life, concentrate on the mass short span bridge. I suggest our Thai railway colleagues should concentrate on your short mid-span bridge instead of one or two so-called star bridges. Give you a word that doesn't make a difference. So a little bit of case study. So you know the short span bridge on the railway, they started with a T girder, then box girder, then a little bit of continuous span cast in place. Why I'm not in favor of a cast in place, especially in the massive construction period, because a good design can be delivered by a good contractor. But if you change a contractor, same thing with the good design, you may be running in trouble. It's called the consistency. Precasting system will give you consistency, but you better have a good design. Because if you don't have a good design, a repetition with a massive amount of waste. Amazing waste. Unbelievable. So the precasting has the durability quality. Its quality is better if you can, because it's all in the shops. Because I worked in the U.S. for about 20 years. I had been a member of their system. Here's my Thai connection. That's 30 years ago. I started working for JMI. My first job is in Bangkok. That's the Bana Bangpre Bangkok job. So that's when I had a connection with Junling. It's a really amazing thing. But then was designed by simple support, then connect later on. Why? At that time, we are not that confident about continuous system because the geometry control for integrated system is much more stringent. It's a lot easier for simple support. I don't think a lot of people can do the integrate system with precast segmental because it requires more precise geometry control. Not only in the casting yard, but also on site, especially the pier segment. So that's that. Then this is the nice frame system, what I call the integrated system in the new German high-speed rail. It's designed by my good friend Stephen Max, who used the chief engineer for German high-speed rail. He's now a professor in Bauhaus. Now, that's 46 meters cast in place. It's a beautiful thing. You know, I trust the German worker can do a good job, but if you're in China or in Thailand, the consistency always in cast in place can be a problem. It's a management issue. Now that's me, and that's Mr. Stephen Max, also our Chinese colleague, all the high-speed rail design folks. And they went further in the new German high-speed rail system. They not only have the longitudinal frame system, but it has the transfers because they want to save a little more concrete. That's something I a little bit different disagreed with my good friend Stephen. Because transversely you have a frame system may save 3% of concrete, but it really slow down the construction time and maybe increasing the cost. So anyway, I'm on the board of International High-Speed Rail Bridge Design Committee. We just published a report. I think you can buy it now, just published. It's labeled clearly. If you can get rid of bearing, expansion joint, do the best to do it. An integrated system is the most efficient system, low carbon system. I'll show you even beautiful system in precasting together. Now I'll tell you why they don't want to do it later, okay? Because they could not copy our big name design institution. So this is some design in Hong Kong in about 15 years ago. It's a good design firm. They also, in a different way, find out an integrated system is much more efficient than a simple support system. Now that's in Macau. We did the geometry control on it because they were so afraid of a cantilever spans out. What if you have a geometry control? It's not right. They may be, going to a different direction when they come to a closure. So you can see what I would like you pay attention is the pier, substructure. Even on the Hong Kong job, they used on the 36-meter span, not 40 meters. They saved 30% of their substructure quantity. You're talking about low carbon, 30% drop. Sorry. Now, in 2004, I designed the first integrated system with precasting technology in Guangzhou Metro. We reduced the substructure, concrete volume, to conventionally in comparison to 40%. Because the span length is 40 meters, already 25%. The pier itself is much slimmer. Even the pier top foundation, piles, everything reduced. Guess what? Their maintenance cost, life cycle maintenance cost, saved 15% compared to the construction cost. $2 million USD per kilometers life cycle. Think about that. That is unbelievable. Think about it, if you have investing $10 billion, saving on the maintenance cost, saving 15%. How much that is? $1.5 billion. What you can do? But that's not even include the social, economic impact. Meaning you close line, the operator has to give you a window to change the bearing. Why? They have to give you a window. Because a window, once in the operation, 2 or 3 hours window is very expensive. They have to mobilize all kinds of operating resource, try to give you that 2 or 3 hour window. So, now that's this is done about designed 10 years ago, in operation about 6 years ago with the design speed 160 kilometers per hour with a 6-car train, double lane. Now we say instead of a twin pier, we put it into the one pier, thin pier, then saved the substructure 50% saving. I mean, all organizations try to, we were joking with Jürgen, they try to have us try not to cook because you may have a carbon dioxide, you may have a dioxide. Boy, the biggest emitter are us. The concrete and steel, number one. No other thing can even come to close. Now, what's nice about these things, you can build with light equipment, with segmental. Instead of you build this with heavy equipment, like 2,000 metric tons of equipment. If a pier, whatever you have a situation, for example, ground piping, or even a little bit of argument. If you stop at one stop, then the whole construction line gets stopped. That is not what you want to do in the complex system engineering. So this is for the little bit heavy rail, 200 kilometers per hour train. We also test this out. It's now been, well, I think it's come close to finish by the end of this year in Guangzhou. Now we propose a new proposal to the high-speed rail. Look, this 350 kilometers high-speed rail with this system. The substructure saving is concrete, 60%. Do you know, if you come close to a simple support system with the high-speed rail, like 360 or 50 kilometers per hour, each appears like a monument. It's not up here anymore. It's amazing. The foundation is massive. The footprint is unbelievable. Footprint. 60% saved in concrete. Not cost, in concrete volume. Cost-wise, top and the bottom, you know, the superstructure, the volume, we can probably save 5%. Superstructure, not that much of a difference. Then the bottom 60%. So you can have a saving for cost overall 10 to 15% cost. That, without saying there's a 15% cost saving in the operation life cycle. How much? You're talking about the overall 30% difference. If you want to spend $10 billion, you can save $3 billion and have a beautiful bridge instead of, I felt, you know, I used to design all kinds of signature bridges all over the world, in Korea, in Hong Kong, in Canada, Latin America, USA. But I felt, to be honest, ashamed of our bridge engineering. How they abuse, how they treat medium to short span bridges. It's like an afterthought. You know, this is for the junior engineer. They're not going to get an award, but that's where the money is. It's crazy. Oh, another thing I want to recommend, you want to see, this is even more sad. You know, whenever there's a geometry crossing the road or something, a little bit of obstacle, what they used to do, they used to use portals. Portal. All kinds of a portal. Like this one, they're going to use 8 portals. The mayor of Shenzhen came to me and said, Dr. Sun, can you please get rid of portal? Otherwise, my citizen will put this entire line into underground, or they get rid of this line. Put underground, 10 times difference. People asked me, why 10 times? The boarding is only 3 times. Well, look at the station. The underground station and the upper ground station, the cost differential could be 20 times if you integrate the life cycle. I don't know if you know the secret. The underground station, in electricity assumption, same capacity, is 10 times more than upper level. Think about it. The construction cost is 10 times on the station. It's not about, 300% is a big waste. At least we don't have to see it. Now the station is 1,000%. That's not including the life cycle cost. I mean, this is crazy. As if somebody wanted to do some earth moving. You know, it's not about engineering design now. So, oh, by the way, this is not a rendering. That's a photograph. Once we did that, our local people, after they had the wedding party, they took a photo underneath the bridge. That's a little park now, instead of ugly number of big photos, Oh, we also do precasting system underground engineering. You know why? I realized lots of the underground engineering does not use pre-stressing. Without the pre-stressing, you cannot do the precasting. How you connect? So they have huge, heavy walls, retaining walls, like 1.2 meter thick, some of them 1.5 meter thick. Oh man, this is unbelievable. We dropped their volume by half by doing precast. They say, oh, what about water? I said, what about water? I deal with water all the time, pre-stressing. So they don't know. It's crazy. So anyway, the advantage I don't have to for precasting, because in Asia, Southeast Asia, then let me finish real quick. Then especially in Thailand, we know precasting, right? So I don't have to repeat it. But it's only the precasting plus the integrated system. If you just have precasting, which is good to clean during the construction, but you don't have efficiency. You see what I mean? Then you still have huge carbon consumption, cost much more. So, oh, by the way, $2 million for a kilometer bridge, life cycle cost, just to maintain the burn whistle and nuts. Can you believe it? So anyway, that's a comparison. That thing looks like an ancient something. That's what we're using now. We have, for the people of Thailand, we started high-speed rail a little late, but that's an advantage because you have a better choice solution. We don't have to repeat a 30 years old, a 50 years old technology, repeat, copy. No. And it's safer. You can see that, get rid of all these puddles. I come here for the past few days. I indeed saw a lot of puddles like crazy, This is that. That I don't have to, but we provide a construction engineering service, not just design, but also for precasting yard for erection, the complete cycle if you need. And that's it. So I wanted just to finish this. There's 2 minute things to share. Oh, more importantly, we provide digital service to make sure you get an error-free precasting. Yeah. So we can share a little more about it because you use people. The most responsible people can make a mistake. You need to have a digital service on industrialized approach. Okay. Last one, I will share with you a little local song for our beautiful number 14 lines. Thank you. No voice. So it can be done, can be a beautiful bridge, save money, save your construction cost, also your maintenance cost.
All right. Thank you. Thank you for your impressive presentation and also the last song. Yes, beautiful. Yes. So now it's time for question. Any question from the floor, please? Yes.
Dr. Sun, thank you for the very impressive presentation. And also the bridges you designed, they are not only very beautiful, but very efficient, And I understand, the span length for the high-speed rail is now 40 meters. I think for high-speed rail in Thailand it's 25. So basically you would have half the number of piers, half the number of geotechnical problems, which are always the problem, when you're stuck, gas pipelines or geotechnical problems, much less land acquisition. You would have much more space for the corridor, for bicycle lanes, walkways, etc. But the most important, much less CO2 emissions, Only for the substructure, 40%, 60% reduction. This is unbelievable. 60, just to have a different construction method, Just to have a different construction method, to have a rigid structure on top and combined with smaller construction equipment. The launchers are much smaller, And if there's a problem, I understand, is that correct? You can just move to the next pier. So you can you're not with a huge launcher. If you have one problem at one pier, I understood, you're stuck. But here, you can just move to the next pier. And could you maybe elaborate a little bit also about the construction time?
Thank you, Jürgen. I think you got to the deeper of the issue. One, if Thailand use 25-meter span length for the high-speed rail, I don't know. If they use 30 or 25, I have no idea. If they use 25 meters, the substructure, we can save more than 60%. If concrete volume, if we use 30-meter span, we can save the concrete volume by 60%. If you have a short span, you save even more. Then back to the construction versatility, resilience method. For the big span-by-span construction, the big ones, each box girder is about, if you use a 30-meter span, it's about 900 metric tons to 1,000 metric tons, including their erection system. It's about another 1,000 tons. So you get a 2,000 ton. So equipment. The girder is actually controlled by construction load. Think about it. What sort of a design you can have a construction load controlling the design? That's one. Secondly, if anything happens with any pier, your whole construction lines get stopped. Even if you have an argument with the landlord or pipeline or anything. But this frame system is all independent because it's cantilever. You can use light equipment to do it. You have a multiple operation area. You can, whatever you choose. Then you can leave the closure joint. Typically, it's like 30 centimeters. Leave it open for the professional closure team. They can come next day, or they can come physically, to be honest, next month. It's irrelevant to the superstructure erection. It's decoupled. It's becoming like a parallel. You got a one team just do the closure. So they know how to do it. Instead of a erection team has to care for the closure. So okay, you may have those team good, but one team good. What about team B? What about team C? What about team D? You see what I mean? Now you have a professional team. They are very good at the closure, continuous tendon. The quality, the speed, the efficiency. Yeah. The elasticity of the construction method is amazing. What we in the Fourth Ring Road in Zhengzhou, I delivered 1.8 kilometer of a bridge in a single day with this system. 1,800 meter of a bridge in one day.
Wonderful.
This is revolutionary, you know. Actually, if this system would be applied, I think 200, 300 kilometer in 2 years is possible.
It's possible.
Yeah, it's possible. So the
You
high-speed
don't have
rail
to
could
have
be here already.
like a world-class heavy equipment. You don't. You can use heavy equipment if you want. Yes.
Okay, I can pick up, an important keyword also, life cycle cost.
Life cycle
Yes.
Yes.
That do the things, yes. All right, any question? If you have no question, thank you very much, Dr. Sun Junling. Please give hands to him.